in this video, I'm going to prove to you how do we get the equation A is equal to V squared over R. And there's another version of it. A is equal to omega squared R, or A is equal to V omega. They're all the same because they come from this equation only by substituting V is equal to R omega. Before we do so, let's derive this equation here. So the few things in circular motion that can be quite tricky for students. One of them is defining all these quantities, right? Angular displacement, linear velocity, angular velocity, right? So the two velocities, this is the linear velocity, that's the tangential one, and this is the angular velocity measured in radian per second. So it's angular displacement over time. So omega is really theta over t. This equation can take another form. If time is one complete cycle, then t becomes time period. The angle you've covered is 2 pi radians. This can also be written as 2 pi f because 1 over t is f. Okay, so if we take this example and we say that this is the radius r and this is the angle theta, then the distance traveled here is s, right? And we know from maths the length of the arc, s is equal to r theta. And if we do say that's the angle covered, so that's a change in the angle, that's a delta theta, okay? And that's the arc that it has traveled. If we divide each side by time, we end up with V is equal to R omega, okay? So that's an easy proof. Okay, so the object is traveling this way. Let's say that's a certain velocity V, okay? And after a certain time t, it's now here. We know that the magnitude of the velocity is the same, so the speed is the same. And what we're going to try and do now is we're going to try and link this up to how we did that earlier. I've just actually enlarged this diagram so it's easier when I do it, it's not too small. So let's go back to this. So this object here is traveling with a certain velocity v, and in a change in a few seconds, it will travel that angular displacement and it will be here with another velocity v. Okay, and we know that this is also r. And what I would like to do now, I'd like to do the same thing. I'll bring that vector down by this much. So effectively, that's v now. That's v, same thing as that, but it's just a bit smaller. And I'm going to pull this vector over here. So that's v. So all I've done, I've just translated them a little bit more, right? That v is now here, that v I've slid it down here. And the reason why I want to do that is because I want to bring that angle somewhere here. And one of the easy way of doing that, let's continue this line, right, is I want you to see that this is a right angle triangle. So if this is delta theta, this would be 90 minus delta theta. This being 90 degrees, this angle then becomes delta theta. So that's a change in theta. Now, this is where we want to be because that helps in the derivation. Now, if we do know that this triangle that I am looking at, you got your V going this way, we're looking at the magnitude, and then the other V is also doing the same thing over here, and that's your little change in the angle. But what I'd like you to know is you started here. That's your V. And there was a change in the velocity. So that's effectively, if you do that in terms of an arc, that's your change in the velocity that brought you to the final point. So you started here and you finished over here. Right? So what we can do now, we can do the small angle approximation. What does this small angle approximation tell you? The small angle approximation tells you for very, very small angles, the sine theta is the same as the tan theta. Well, what does it mean? If you take your calculator, you type in sine 1 degree, and you do the same tan 1 degree, it'd be roughly equal to 1. So up to around 10 degrees, this approximation is very good. And what are we doing? We're assuming that the radius is quite big and the angle is very small, so this approximation can be used, right? Now, if we now do our tan theta, so that's our angle, and if you do look at it, I've effectively got that as my sort of 90 degrees if I want to look at it like that. So that's my opposite. So tan theta, in this case, is a small change in theta is equal to the opposite, which is the change in the velocity, right, divided by my hypotenuse. Whichever way I look at it, is v anyway. And applying the small angle approximation, tan for theta that's very, very small, right, tan theta would also be approximately equal to change in theta. And if we send this velocity to the other side, we'll end up with something like this. What can we do now? If we divide both sides of the equation by change in t, this is what we end up having. Change in theta over t, that's omega. Change in velocity over time, that's acceleration. So that is it. Proved.